So in chapter 11, we look at the different types of chemical bonds that can form between different atoms and the different types of compounds that can be created as a result of those bonds. But before we can do that, we need to have a look at what we call the periodic trends in atomic properties. So just reviewing the periodic table again, we know that metals are on the left of the periodic table and make up most of the periodic table. In this periodic table, they're kind of indicated in this sort of, yellowish sort of color. And the key property of metals is that they tend to lose electrons to form cations. And the types of compounds that metals form are ionic compounds where they combine with non-metals. So metals form ionic compounds. In those ionic compounds, the metals are present as cations. The ionic compounds are formed between metals and non-metals. Now, non-metals are fewer on the periodic table. They're indicated here in this kind of greenish color. And non-metals have the tendency to form anions, that is, they like to gain electrons. And so when non-metals combine with metals, they form ionic compounds. The metals will be present as cations, the non-metals will be present as anions. But non-metals also participate in another kind of bonding, and this bonding is called molecular or covalent bonding, and that exists between non-metals themselves. So non-metals combine with other non-metals via covalent or molecular bonding, and those two words are used interchangeably, covalent and molecular. They're synonyms, they have the same meaning. And so when non-metals combine with other non-metals, they form what we call molecular compounds as opposed to ionic compounds. And what differentiates ionic compounds from molecular compounds is the type of bonding present in those compounds. So we saw that the electron configuration of the elements varies in a periodic fashion across the periodic table. And as the arrangement of electrons in an atom is what determines its properties, we would also expect that the properties of atoms vary in a systematic fashion across the periodic table. Now, the first property that we're going to look at and how it varies across the periodic table is atomic size. So how big an atom is. Now, it's important to realize that we'll often model atoms as being hard spheres, but that's not really what they are. They're kind of fuzzy little balls of with electrons on the outside, and the position of those electrons is kind of a little bit uncertain. So modeling them as hard spheres is not entirely accurate, but that's what we tend to do. And it's also worth recognizing that how we determine the size of an atom is by looking at how it behaves when it's combined with other atoms or even atoms of itself. So the important idea there, though, is that when an atom engages with another atom, how its electrons are moved around will depend upon the nature of the atom that it's interacting with. So you're going to see slight disagreement in reported sizes of these atoms depending on how they were determined, but don't get too hooked up on that. So the first thing to recognize is that as we go down the periodic table, we're moving, every time we increase the period, we're adding another layer of electrons. So it is not surprising that as we move down a group and we increase in period, that the atomic radii of the elements gets bigger. So that's our first trend, is as we move down a group, the radii of the elements gets bigger. And that's just simply because we're adding another layer of electrons every time we move down a period. As we go across a period, the trend is more subtle and also sort of slightly more awkward to explain. It's important to realize that as we move across a period, all of the electrons that we're adding to our atom are going into the same shell. So that shell is at approximately the same distance from the nucleus for each of the atoms in that period. But what is changing as we go across the period is the atomic number is increasing, which means we have more protons in the nucleus, and the effect of that is that it pulls all of those shells in a little closer. So what we see as we go across a period is a slight decrease in the radii of the atom. which is representing that all of those shells are just kind of being pulled in a little bit more by the increasing nuclear charge. Now, this effect is sort of minimal for the transition elements, and I'll show you some images of the atoms in their sizes a little later on, but this is in period 2 and you can see the trend, it follows it perfectly. So this would be a typical kind of question where you're asked to rank atoms in order of increasing atomic radii, and I found one of these nice periodic tables that has images of all of the atom sizes, but the important thing to recognize is this, that they get bigger as we go down from fluorine towards francium, so they get bigger. Okay, so these are the 4 that we have to rank, so let's identify them by period and group, because that's what's going to identify, that's what's going to determine the size. So we got sodium and potassium. So potassium is lower than sodium, so potassium is going to be bigger than sodium. So we've got 2 metals there. And then we've got chlorine and argon. So here they are over here, chlorine and argon. So chlorine is going to be bigger than argon because chlorine is to the left of argon. Now, what about in this? So chlorine and argon are in period 3 along with sodium. So the whole sequence is going to go sodium, chlorine, argon, because we've as we go across period 3 they're going to get smaller. And then potassium is going to be bigger than sodium, so there's our sequence. So you just got to kind of logic your way through it. So it's going to go potassium, sodium, chlorine, argon. Potassium's in period 4 way over to the left. Sodium's in period 3 way over to the left, and then chlorine and argon are also in period 3. So all of those that are in period 3 we just listed left to right. Okay. So every now and then you'll hear people talk about ionic radii, and ionic radii is the size of a cation or an anion, and again it's measured normally from a compound. Now all ionic compounds are crystals at room temperature, and it turns out that crystals are really good at scattering light. So if you take a crystal and you shine in particular X-rays at it, those X-rays will scatter, and we can take a photo as to the angles they're scattering at, and we can work backwards and we can get the positions of all of the atoms in that crystal. So if you've ever seen a picture of a protein or a virus that was perhaps used to develop a medication, then they would have figured out the structure of that protein or virus using this technique. So we do this all the time, and it's really, really, really helpful. Now, when it comes to ions, it's important to realize a few things. Cations are formed by the loss of electrons. So a sodium atom will lose 1 electron and form a sodium ion. So it makes sense that they are smaller than the atoms that they are made from, what we call their parent atoms. Now, anions are formed through the gain of electrons. So it makes sense that anions are larger than the atoms that they're made from. And then the only other thing that we have to remember is ionic size will increase down a group. So what we see is that as we go down a group, the ionic size increases just like it did for the atomic size. So here's the atomic size increasing going down a group, and then here is the cation size, and you can see the cations are smaller than their parent atoms, but they still increase down a group. If I go over to the anions, here are the parent anions, the neutral atoms, and they are increasing in size down a group. And then underneath we've got the parent anions, and they too are increasing down the group, but you can see that the anions are bigger than the parent atoms. Now as we go across a period, what do we see? Well, we see that in any given period, the anions in that period are always bigger than the cations, we see that the cations do decrease as you go across the series of cations, and we see that the anions also decrease as we go across the series of anions. So it's a little more complicated, right? But the important thing to recognize is in any given period, the anions are always bigger than the cations. The cations decrease in their own sequence across that period, and then the anions also decrease in their own sequence across that period. So we've done a good job of talking about how atomic size varies across the periodic table, and it's effectively like that. They get bigger that way on that diagonal there, fluorine to francium. And now we're going to talk about a more obscure property. It's called the ionization energy. And so the ionization energy of an atom is the energy required to remove a mole of electrons from 1 mole of atoms. So the first ionization energy removes the outermost electron from the neutral atom. So you take the atom, remove 1 electron by putting some energy in, and you generate an ion, a positive ion, because we're removing an electron. And the energy required to do that, the change in energy of the atom to make that happen, is called IE1. It's called IE1 because it is the first ionization energy. Now, if I take the ion formed in that first step and I remove another electron, then I'd get a 2+ ion, and you guessed it, the energy required to remove that second electron is called IE2. So we could define IE3, IE4, and so on in that way. So IE3 would be taking the 2+ ion and making the 3+ ion by removing an electron, and that would be IE3. So remember that for IE1, we're taking an electron away from the neutral atom to make a positive ion. And then from IE2, we're taking an electron away from the positive ion, the +1 ion, to make the +2 ion. And for IE3, we're taking an electron away from the 2+ ion to make the 3+ ion, and so forth. So what we'll see is that the ionization energies will get bigger and bigger. That is, IE1 is smaller than IE2, smaller than IE3, and so forth. And the reason is because you're removing the electron in those higher ionization energies from a positively charged ion, and it's getting worse and worse and worse as you remove more and more electrons. So the ionization energies get bigger as you remove more and more electrons. Now, there's a pretty simple pattern in the sequence of IE1. So the closer that the electrons are to the positive nucleus, the harder they are going to be to remove, because remember, the electrostatic interaction increases as distance decreases. So as atomic size decreases, IE1 will increase because the electron is held more strongly by the nucleus. So how does atomic size decrease? Atomic size decreases from francium up towards fluorine. So that is the order that IE1 increases. Right? As the atoms get smaller, it gets harder to remove an electron. So what we would expect is, as we go across a period, IE1 will increase, and as we go down a group, it will decrease. So let's have a look here. So these are the group 1 elements. And what do we see? As we go down group 1, IE1 decreases. Now, what about as we go across a period? Well, as we go across a period, here we go, we're going lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. What do we see? As we go across a period, in general, it increases. Okay, here's period 3, goes sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. Right? Going across there. And it increases. There's some lumps and bumps in there that we're not going to tackle why we see that in this group, but you can see that the general trend is as you go down a group, the ionization energy decreases, and as you go across a period, it increases. So here's another group. This is period 8, helium, neon, argon, krypton, xenon, radon. You can see that there's a decrease as we go across there. All right. So it seems to be pretty consistent. So in general, ionization energy 1 increases from the bottom left of the periodic table towards the top right. Francium to fluorine, increasing IE1, and that's also decreasing radii. Okay, so you can get these nice periodic tables that have all of the IE1 values listed, and it's worth looking at them, and what you see is that metals have much lower IE1 than non-metals, and that explains why they readily form cations. So let's just pick out, stereotypical metal would be something like sodium, and a stereotypical non-metal would be something like oxygen, and you can see that the oxygen has a much larger IE1. So non-metals have really big IE1s, and they don't actually like forming cations. They don't form cations. What they like to do is form anions. They actually like to gain electrons rather than losing them. Alright, so worth having one of these tables handy, or periodic tables in different forms are worth having handy. So let's have a look at some Alex type problems and see what's going on. So it says reorder each list in the table below if necessary, so the atoms or ions are listed in order of decreasing size. So in the first row here, we've got an anion, and I know that an anion is always bigger than its parent atom. So the chloride ion will be bigger than the chlorine atom. And then I have to think about where chlorine is relative to argon, and they're in the same period, and we know that as we go across a period, we get smaller. Okay, so that means that the chlorine is going to be bigger than argon. So my sequence would be chloride, chlorine atom, argon atom. Okay, so that's the first one, not too bad. The second one, oxygen, boron, carbon. So the first thing I'm going to do is locate all of these guys on the periodic table. Okay, and they're all in the same period, and we know as we go left to right, they get smaller. So we're just going to list them left to right. So boron is bigger than carbon, which is bigger than oxygen. So that wasn't too bad. We've only got one left. Barium, calcium, strontium. Okay. Barium, calcium, strontium. They're all in the same group, and we know as we go down a group and get bigger. So in order of decreasing size, it's got to be barium is bigger than strontium is bigger than calcium. So these are not too bad, pretty straightforward. Just got to remember the two patterns, one for going across a period, one for going down a group. Okay, so that concludes section 11.1, and just let me know if you have any issues with anything.